Function notation. So we need a way for us to indicate that a relation is a function, and a way for us to show how to evaluate the function at any given value of the independent variable. So in other words, I want to ask that question that says, what is the y value given some x value? And we have some notation that asks that question in just a few letters. And it looks like this. F of x, function notation. So suppose we have a function, okay? So we're going to let this letter f, that's going to denote that given function, okay? And what you see inside the bracket, that is our variable x. And we're going to let x represent that input value. So what does the whole thing, f of x, so f of x, that whole thing, f of x, we call it f of x, okay, denotes the entire value, the output of the function when x is the input. In other words, when you see that equation that says y equals something, we are now replacing that y with f of x. So this is just a way for us to say, I want you to find the y value when the input is x, whatever that number x is. Okay, so this is what we call function notation. Okay, and again, we call it, the way you read it is f of x or f at x. So how do you understand this? So f is just the name of the function. It's not a number, it's just a label. You can call your function f, you can call it g, you call it any letter in the alphabet can be used. Okay, so on the left side, you just have that function, it's a label, it's a name. And every function has an input value. So that x is what we call the input value. Okay, and so on the left side, you're not evaluating the left side. You're not multiplying anything here. This whole thing is just saying, this is your output, this is your y, this is what your y is going to be. Okay, so you're not multiplying f and x. There's no number here for f. It's just a label, it's just a function. The input is my x. The actual math expression is what's on the right side. So the math expression that tells you what to do with the input value in order to produce the corresponding output. Okay, so again, the proper way of stating this is f at x or f of x. So if you know your familiar linear functions, y equals mx plus b, you can now write them as f of x equals mx plus b. And similarly, with the quadratic ax squared plus bx plus c, you can write that now as f of x equals ax squared plus bx plus c. So we're going to look at questions throughout the rest of the semester and in the rest of your math courses in the future. Are going to have function notation. F is not always going to be the letter that's used. You could have G, you could have H, you could have V, and your inputs could be different as well. It may not always be X. It could be D for distance. It could be T for time. Okay, but all these letters are used to distinguish different functions and their inputs. So let's evaluate some functions. So example 1, let's determine each value. So I have here the function g, and I'm asked to evaluate it with an input of 3. So the graph here on the right, this is your function g of x. So now you're replacing the y value with g of x. And so if I'm going to evaluate the function g when x equals 3, I'm looking for x equals 3, and I'm going to the graph, identifying the point on the graph when x equals 3, and I'm trying to figure out what is the output. So what's the y value, in other words? So the y value is 2. So I'm just saying, find the y value when x equals 3. That's all function notation is doing. And it's just asking that question with just a few characters. So I don't have to write out that entire question that says, tell me the y value when x equals 3, right? Just understand when you see this notation, that's what that is telling you. So I'll write it here. So find the y value when x is 3. So why write out all those words when we've developed function notation that will tell us the same thing? So g of 3 or g at 3 is equal to 2. Okay, what about g when the input is -1? So you look at your graph for -1, find the point on the graph. There it is. It's on my x-axis. So that y value is 0. So in other words, when I evaluate g at -1, the y value is 0. Okay. Now, what if you're told the y value? What if you're told the function evaluates to 1? So here is 1. Where on the graph is y equal to 1? It's right there when x is 0. So what is x when g of x is equal to 1? Well, x equals 0. So in other words, g of 0 is equal to 1. Okay, so let's find the domain and range of my function g of x. So it's this graph right here. It starts at -1 and it goes to the right. So for my domain, I can say my domain, x is the element of all real numbers. I don't see any skips anywhere. It's a continuous curve. So x is the element of all real numbers such that x is a number greater than or equal to -1. And my range starts at the y value of 0 and it goes up. So my range has no negative y values. So I'll say y is the element of all real numbers such that y is greater than or equal to 0. Okay, let's look at another example. Let's see how we can evaluate functions. So consider the functions f of x and g of x. Now they're given to us as equations. Let's find the following. F of 5 minus g of 5. So this question is asking me to evaluate f of 5 and evaluate g of 5 and subtract those two y values. So let's do f of 5 first. So f of 5 equals, substitute your input x with 5, so 5 squared minus 3 times 5, and that will be 25 minus 15, which will give you 10. Then I'm going to evaluate g of 5. And g of 5, look at the function for g, it's 1 minus 2x, so it's 1 minus 2 times 5. And that will be 1 minus 10, which is -9. And now I'm going to evaluate f of 5 minus g of 5. So f of 5 minus g of 5 tells me I'm going to just subtract the two values that I calculated for my expressions here, 10 and -9. And when I do that, I'll have 10 minus -9, which is positive 19. And there's the answer. Okay, part B. What about 2 times f of x? Okay, so this says multiply 2 times f of x. So 2 times the function. What's my function? X squared minus 3x. So I'll just use the distributive property and I'll get 2x squared minus 6x when I simplify it. Now your input could also be a combination of a variable and a number or an actual expression, g of x minus 2. This says, so take your input x minus 2 and replace wherever you see x in your expression. So I see x right there. Replace that with an x minus 2. So I'm going to say g with an input of x minus 2 will be equal to 1 minus 2 times whatever my input is. So that x is replaced with whatever your input is. My input is x minus 2. So think of that x as a new x, it's a different x minus 2. Okay? And if I simplify that, I get 1 minus 2x minus 4. So I'm distributing the 2 with each of the terms inside. Simplify that one more step. So negative 2x. 1 minus 4 is negative 3. So negative 2x minus 3. You can also add functions together. So I can add f of x and g of x together. So if I take f of x, I'll have x squared plus x squared minus 3x added to g of x, which is 1 minus 2x. And I collect like terms. And if I collect like terms, I'll have x squared minus 3 and minus 2 become minus 5x and plus 1. Okay, what about g of f of x? So this says take your function g, and as your input's going to be f of x. So what's f of x? F of x is x squared minus 3x. And so wherever I have an x, if I write out g of x, what's g of x? Whatever I do when I write out g of x, I write 1 minus 2 times my input, X is the input, remember? So where I have my input, I'm going to replace it with f of x. So this f of x goes in there. X squared minus 3x. And then I expand. So 1 minus 2x squared, and then plus 6x. And if I just rearrange the order, I'll have minus 2x squared plus 6x plus 1. And I like to write things in order with the highest degree terms first, highest to lowest. Okay, example 3. So company rents cars for $50 per day plus 15 cents per kilometer. Express the daily rental cost C as a function of the number of kilometers D traveled. Use function notation. So the old way of doing it would be to say, okay, my cost would equal, well, $50 per day plus 15 cents per kilometer. So D is going to be the number of kilometers used. So that's my variable. And so my unit rate is 15 cents per kilometer. So 0.15 times D plus a flat rate of $50. In function notation, I'm going to change the left side where it says function C, whose input is D in brackets. Okay, so that's now function notation. But when I evaluate this for any value of D, my end result is just the cost. It's just going to be C. Okay. So if I'm asked to determine the rental cost of driving 472 kilometers in one day, I'm saying here that what's the cost when my input is 472. So if my input is 472, everywhere that I have in my expression on the right side, where I have my D value, my input, I'm going to replace that with 472. So 0.15 times 472 plus 50. And that's going to have to be evaluated. And so you might need a calculator for this one. So when you evaluate 0.15 times 472 and add 50, the end result should come out to be $120.80. Okay, so determine how far you can drive in a day for $80. So now my cost is equal to $80. Replace your C of D. So I should be more accurate here. C of D equals 80. So I'm going to replace 80. And then on the right side, I have 0.15 times D plus 50. Solve for D, solve for the number of kilometers. And if I subtract 50 from both sides, I'll have 30 equals 0.15 times D, and D will equal 200. So D equals 200 after I divide both sides by 0.15. So therefore, you can drive 200 kilometers with $80. Okay, and that's function notation, and that ends this lesson.